I'm going to go ahead and get started with this session. Since we just have an hour and a half, we're going to try and squeeze in quite a bit. So first of all, thanks everyone for coming. Hopefully you all had enough time for lunch, and we really appreciate you coming to this session. There's a lot of interesting parallel things happening at ESIP, it seems. So thanks for your interest in Pangeo. And our hope today is that everyone's going to get some hands-on experience using some demonstrations and example workflows, but also some time just to experiment on your own. And for the last half hour of this session, we'll kind of be roaming the room and just letting everyone experiment with these tools that I'm going to showcase today. So on the Sketch website, or the ESIP summer meeting, there is a link and an agenda down here. I've got that we'll be spending about 10 minutes doing a quick introduction to Pangeo. And there's a link to some slides. So if you all want to follow on your own, you can use that link. Otherwise, these are the same slides that I'm showing here. 10 minutes is a bit ambitious, I have to say. We've got about 20 slides. So some of these I'm just simply going to skip because I think people are more interested in getting a hands-on experience being a workshop session. So my name is Scott Henderson. I'm a research scientist at the University of Washington. I work in the Earth and Space Sciences Department and the eScience Institute. And the co-conveners of this session are sitting at this table over here, Amanda Tan, Anthony Arndt, and Andrew Poloski. We're all gonna be helping out today and roaming the room. So you'll see pictures of them, or just approach them. You now know who they are if you have questions throughout this session. And we also put sticky notes on the tables. Because it's a workshop session, we figured people will have questions, but because of the lack of time, it's just helpful to put up a sticky note if you have a question, not to interrupt the flow of things, but then we can roam around the room and help you out. So if you need assistance or you just want to ask a question on the side, that's what the sticky notes are for. Just go ahead and put it on your laptop. So I'm going to spend about 10 minutes just talking about the Pangeo project and introducing it to people in case you haven't heard of it before. And the organizers of this conference asked that each session have kind of 3 takeaway points. And so these are the takeaway points from this workshop that we hope you will come away with. So first of all, is that Pangeo is not a single platform. It's not a single website that you go to and log in to do your analysis. If folks have utilized Google Earth Engine before, or some of these other platforms, it's not quite that. It's really a coordinated community effort to develop open source software in a cohesive way. So the second point is that the major goal of this effort is to facilitate scientific computational workflows on both cloud and HPC systems and overcome major data management bottlenecks that we're currently facing as a research community. So one of the main ones is downloading large amounts of data as these archive sizes grow. And the third point is that there are various ways to use Pangeo JupyterHubs, which I will demonstrate today. And we're always looking for more people to get involved in this community, and that can take on many different, that can be done in many different ways, which we'll also describe. So I'm coming at the Pangeo project from the perspective of a researcher that utilizes NASA satellite imagery. And we have a project that's funded by the NASA Access Program to develop some of the tooling that had already been constructed through an NSF EarthCube proposal, utilizing JupyterHub and many Python libraries to work with data where it's stored rather than download data locally and work with it on our own workstations. So this schematic that you can see up here on the slide is sort of illustrating how this works in effect. Really key to this functioning is utilizing JupyterHub as a tool. So this is a means to kind of deploy an infrastructure and a user interface where data is stored. So this is, here we have got the cloud, but it could be an HPC as well. And we're focused really on Python libraries, but as we'll discuss, there are other options. this is largely motivated by the growth of these data archives and the fact that researchers are now no longer able to download large amounts of imagery in the case of NASA products. So this Access project, as I mentioned earlier, is a team effort involving people at University of Washington, but also other institutes around the country, and also folks from companies and professional software engineers. So we think it's a really powerful collaboration to have people of many different backgrounds working on this project together. So the science use cases really motivate how software is being developed. So if some of you were in a session earlier on big gridded data, you may have seen this same slide, but the architecture is really set up to utilize a few key technologies. First is that we have data stored somewhere readily accessible in an appropriate format. So on the cloud, this is going to be S3 storage, object storage. And then the architecture that we're using to work with that data is based on key Python libraries. In this case here, we're showing Dask in concert with Xarray to work with multidimensional gridded data. I'm not going to get into the specifics of how this is actually deployed, but I'm happy to talk about that with people later if you want to understand the underlying architecture. For cloud and HPC deployments, we're using containers and running on Kubernetes. So we focused on Python because we feel like it's really had a lot of uptake in the scientific community. There are a lot of core packages out there that are extremely useful for day-to-day work and scientific analysis. So here we're just illustrating Python's sort of the foundational elements. And then as you move out in this diagram, you're getting into more and more specialized software packages that people use either for oceanographic applications or satellite remote sensing applications, machine learning packages, etc. And one of the aspects of the fact that this isn't a single deployment, but rather a collection of tools kind of built to work well together and built on Jupyter is that you're not even limited to Python necessarily. You could be running R in the same way. It just takes some effort to utilize some of the tooling we've developed to deploy this and plugging in different packages and different software languages that work well with the Jupyter project. So I'm gonna, like I said, I'm just gonna have to skip some of this because we have a lot of material in these slides. But I do think it's worth mentioning in this community with ESIP that some of us are right now really focused on applications with NASA data. We're about a year into this project, so there's still ways to go. But one of the key things we're working on now is thinking about how we can better ingest data into our workflows. So we're using the common metadata repository as sort of a building block to discover data and trying to integrate it with stack catalogs, which we also maybe heard about in another session this morning if you were in the big gridded data session, to facilitate not searching, discovering, and downloading, but searching and then immediately loading into some in-memory object that we can run code against. So rather than show static examples, I'm going to skip a few of these because we'll run hopefully all these examples together dynamically. But just as a show of hands, I'm curious to know which examples to focus on today. So how many people work with Jupyter notebooks in the room? Okay, majority. And how many folks have worked with Xarray or Dask? Okay, so yeah, generally, Xarray is extremely useful for uniformly gridded data, multidimensional data. So there are a lot of examples that have been demonstrated with climate modeling datasets, for example, but it also turns out to be a very convenient format for satellite data. And the data model is really multidimensional gridded objects. And so here kind of we're seeing loading a single raster image, in this case a Landsat image, which is stored as a cloud optimized GeoTIFF. You can also load ZAR datasets. Anything that is a NetCDF or HDF dataset works very well to load into an Xarray object. And The general conceptual model is illustrated down here, where you have some sort of variable of interest, be it temperature, precipitation, or some band index for a raster image. And you have coordinates, in this case, latitude, longitude, and time. So you can have multidimensional labeled data with an X-array object. And it's represented in memory. This is just a text printout of what an X-array object looks like for this raster image, where you're not referring to things as 0, 1, 2 axes, but rather the latitude axis, the longitude axis, the time axis. And so it's a nice way to interact with your data sets. And Dask is for distributed computing in Python. And you can see in this line up here that's describing our array, in this case, the image, that we've specified chunk sizes. The image has a full dimension of about 9,000 by 9,000 in terms of latitude and longitude pixels. We break that into specified chunks with Dask. And that's all you have to do as a coder or researcher working with this image in order to parallelize it, which makes this library very powerful. You specify the chunk size, and then Dask is going to farm out operations to distributed machines that you have available to you. So again, I'll just mention, we're really focusing in this project developing and improving existing libraries that are already pretty well established in Python and making them work well together. So X-array, Dask, and Intake is a new library we're focused on to bring data stored in object storage on the cloud into Python pretty easily. Okay, so where can you run these JupyterHubs and these Jupyter notebooks? So there are a couple places right now. We have 2 deployments that we've put together over the last year. One is a sort of dedicated system that has persistent storage for users. And that's more familiar to those of you that have used JupyterHub on your laptop or run Jupyter notebooks locally. Your files are going to stay there. And every time you log in and log out, machines are spun up and spun down, but the disks are persistent. So we have one of these deployments running on Amazon Web Services at nasa.pangeo.io. And if you're interested in having access to that, we can add you to a GitHub organization in order to access. Just see me afterwards. The other way we're able to deploy this infrastructure is using the binder technology that's been developed as part of the Jupyter project. And that's what we're going to use today for these demos. And so one thing, really important thing to keep in mind is that this is not a persistent system. This is meant for demonstrations. And so you log in, you can save files locally, but as soon as you shut down your browser tab and log back in later, anything that was local is going to be wiped. So just keep that in mind. Okay. Also in these slides, there are links to some other tutorials that we've given in the past. Being just an hour-long workshop, really, there's not a whole lot of time to get into the details, and so these links we hope that people will, refer back to, and you can, when you have more time later, look at some webcasts and explore some different demonstrations. And finally, we're also running these hubs to support Hackweeks at the University of Washington. So these are week-long kind of investments in learning these tools. And there's some links to upcoming ones on this final slide here. So I think with that, we'll just jump into some demos because there's no better way to learn this stuff than to get some hands-on experience. So on these slides, as I mentioned before, if you came in late, these slides are linked on the Schedule page for this session. You can find 2 links. First is this introductory materials link. So if we click that, we'll be taken to a GitHub repository. And this is a tutorial repository. You can read this information about, again, some details about the packages we're using, but this button here that says Launch Binder will actually bring you into an interactive computational environment. So I'm going to click that that button. And this brings us to the following page, which shows that things are spinning up. So this may take a while for people in the room to actually be dropped into a JupyterHub session. The reason for that is that as soon as you click that button, machines are being spun up on Google Cloud. And so it can take some time, especially if there are 60 of us all requesting machines at the same time, for those machines to provision for people. So there is a spinning wheel, but be patient and you'll drop into a session momentarily. So I'll point out as well that if instead of clicking that button, you're to go to the following website, binder.pangeo.io, this kind of describes what's actually happening behind the scenes. So this is a landing page for a service that we've actually set up on Google in this case, which turns a GitHub repository into a JupyterHub image. And so the way this is working is you have your notebook that you've created along with an environment file that describes the Python packages you're using. And you put that on GitHub, and then it's just a matter of putting in the GitHub link on this page, and then you can fire up an interactive session. So this is great for kind of interactive, I guess, shareable work with colleagues. You don't have to set up accounts. You don't have to really know what's happening behind the scenes with the cloud infrastructure. It's been sort of set up to be user-facing and just easy for people to get experience with. So, has anyone successfully been transferred from the spinning wheel into another session? So a couple people. That's good. I have not. So I should have made sure to click it first myself. But we'll just be patient. If we go back to the slides, you should see a second link down here, which is Landsat 8 analysis on AWS. And so if people go ahead and click that link as well, you end up in another GitHub repository. At the bottom here, you'll see two buttons. One is to launch on Google Cloud. The other is to launch on AWS. And so we want to launch this one on AWS. And so you'll click that bottom button to do that. So you'll see it's pretty much the exact same interface. There's no difference really between running these things on Google Cloud or running it on Amazon Web Services. In fact, there's another web page you can go to that's aws-uswest2 binder.pangeo.io, and it just looks the same. So the kind of a major impetus to this project is to develop things that are portable between different cloud systems and between HPCs, but that have the same user interface. All right. Problems with live demos, I suppose. Just a quick show of hands. How many people have successfully opened one of these? All right, we're getting there. This is good. Great. So another thing then, while I'm waiting for my own to open, is we will, oops, excuse me. Sorry. I'll just spend a little bit more time illustrating how this binder system works behind the scenes. So this button that we've all clicked on and now we're waiting for things to load is reading information in this GitHub repository. So we have in here a folder called notebooks, and you can see these different notebooks, Xarray, Dask. These are introductory notebooks designed to illustrate how to use these Python libraries if you're not familiar with them. There's also a few more sophisticated demos. So there's an ocean sea surface height demo and a demo using Landsat 8 data. So you can copy links to these notebooks and go to a site called NB Viewer on Google. And you could put a URL to any notebook. Into a service like NB Viewer, and you'll see the Python code there. So the difference between what we're doing with something like this is that it's rendered statically, right? So you would have to download this and install your own environment if you wanted to run it. But this is a nice way to just visualize if you're just simply interested in looking at a notebook and seeing kind of Python code behind it, you can look at things statically this way. The binder's still not launching for me, unfortunately. But once it launches, you're in a JupyterHub session and you can open those notebooks and run them, start to run them dynamically. So I'm gonna wait just another minute or two for this thing to launch. In the meantime, maybe we'll take just a couple questions from people, if anyone has questions so far.
So how is NB Viewer different than just like opening the notebook in GitHub?
It's not in theory. I've found that sometimes you click on a notebook in GitHub and it doesn't necessarily render. So I just clicked on this one and it's, I don't know.
Is that based on size or?
I'm not sure why,
Oh, okay.
to be honest,
Thanks.
but yeah.
I was just saying that NB Viewer renders the JavaScript, whereas GitHub doesn't always render the JavaScript.
Oh, then it won't record.
Oh.
Let me just try and launch again.
Hello, do you get better performance on AWS out of curiosity? Like if you're actually paying for resources?
So performance-wise, we honestly haven't done a lot of benchmarking, but
I don't actually necessarily mean performance, just responsiveness, I guess.
So I can't really say, to be honest. I haven't noticed any significant differences qualitatively.
So
but
for example, in this example, you have my binder, which is responding so-so, and then you have AWS, which, do you get more responsiveness on AWS perhaps?
I would say it's on par, really, in terms
Okay.
of responsiveness. Unfortunately, yeah, I'm not sure why it's taking so long to launch for me in this case. It's usually quicker, but then again, we haven't really stress tested this in many situations with 60 people hopping on at the same time.
I think everybody in this arena is sort of dealing with the same issues. I certainly am in what I'm doing.
Yeah.
And we'll talk about that tomorrow.
Sounds great, yeah. So I have noticed, yeah, if it's okay with people, I think we may plug into a different laptop, which means that we'd lose the screencast, but okay. Yeah, if you see errors, Rich is saying don't worry about them currently.
Quick question.
Yep.
My administrator has blocked my ability to open NB Viewer. Can I still participate in this?
You know, I haven't seen that before, so I'm not sure with folks who are dealing with firewall access, et cetera.
It's off. You could get yours, right?
There should be plenty of
I
room.
mean, you know, it's not scaling up like someone who could drop off, you could grab them, right?
Yeah,
But so everybody else.
yeah. Another quick poll here. How many people have this spinning wheel instead of actually seeing a JupyterHub session? So it looks like maybe I'm the only one at this point.
You want to reload?
Yeah, I'll try and let me just fully shut down and try to.
Is this like, see all these guys here, just like, does that?
I'm not sure. Yeah, it might have to do with some sort of browser issue on this particular computer.
Just a second. I don't know where in the room here.
Anthony, art presenter.
Oh, okay. Okay. Then yes, you can.
Okay, so I can just plug in.
You can just plug that in.
I need a HDMI.
Do you have? So this is the VGA. This is not HDMI.
No, I don't have it.
Yeah.
How's it not doing? It's just not loading your.
There's no link, so they try to change your computer.
Okay. Do you want to change out the computer?
Yeah, I think that's probably the quickest.
Okay.
And I
What kind
just
of
need a
input do you have?
HDMI.
We don't have HDMI on here. This is VGA, so
I'll try and do it with a different
Yeah.
browser.
try and get you. How's your internet connection?
Is there another browser
To me,
besides Chrome?
yeah. We should probably find one. Let me just see what that connection is good. So I'm not going to take you off of that. I don't know if they have any browsers that are on here. Have you tried to close out of it and go back in and different things?
Yeah.
It's not.
Seem to be working.
So we don't have HDMI.
I can get an HDMI. Just take me a few minutes. That's what we want to do.
Maybe we can like still loading at this point, and then maybe they can get HDMI in the same time.
Should we ask the room?
Yeah.
If someone has one.
Yeah.
Does anyone in the room have a VGA to HDMI converter? Worth a try.
before? And so
We have to the go-to meeting, unfortunately. So yeah, you do have HTML.
Does he have to go to meeting on this?
that,
Is that what it was?
And then you can just share your screen and you can just tell us. Does that sound good?
Okay.
they can do the presenter. They don't need to have
There it is.
its own.
Perfect. Thanks. Yeah.
I'm pulling up your notes. Like, I don't know which shooter.
Okay.
Yeah.
Perfect.
Okay, go ahead.
Okay. I think we've found a solution, thankfully. It seems like there's some issue actually with the browser on this particular laptop because everyone was able to log in, is the impression I got. The Pangeo demo tutorial is the first one we'll look at. So that's actually good news to me. I was worried that no one was getting in, but we'll work through it. So everyone should now see something. Make this full screen, hopefully it's a bit bigger. Something like the following. After you click on that binder button and you get a spinning wheel for a bit, you're plopped into a JupyterLab interface. So this should be very familiar to those of you who've used JupyterLab on your own laptops. The key difference is that it's running, in this case, on Google Cloud. So you have the same user interface, but the machines behind the scenes are on cloud infrastructure. So in this tutorial, there's this folder notebooks, which is the exact same folder that I pointed out earlier on GitHub. So all these materials are now available, but they're available to you in an interactive way. So if we choose one of these notebooks, we have until 2:15, I believe. So thank you. Thanks. So it seemed like not about half the room maybe had seen Xarray before. So I'm going to go ahead and open this xarray.ipynb notebook to just walk through a few examples of how Xarray works. Rich was mentioning earlier that some of you immediately noticed these 404 not found errors showing up on the right-hand side. And that's because we haven't really opened Dask yet and launched a Dask cluster. So not to worry about those. In fact, we can just go ahead and close those for now, those tabs. So now you have this notebook. Notebooks are great. It sounds like I don't need to really go over how notebooks work because many people in the room have used them before. But you have different cells that have markdown and code, Python code in this case. And to run particular cells, you can do a Shift-Enter. Once you get to a cell that contains Python code, running Shift-Enter is actually executing that code. So this first cell in the Xarray notebook is bringing in tutorial data to work with. In this case, it's sea surface temperature data. So this notebook is really designed to introduce people to Xarray from scratch. I think it's helpful for just walking through how Xarray is set up as a data model. So we'll actually start by just creating some synthetic data, one-dimensional data. In this case, it's a sine function. And people who've worked with Python in the past will recognize that we're making NumPy arrays here. There's a question in the back. I'll try and make this a bit larger. That's too large, probably. Is that all right? Is that a bit better? Yep, so we'll bring that over. Hopefully that's a bit larger for everyone. So, so we've created some arrays of data here. In this case, F is going to be our values and X is really our dimension and our coordinates. NumPy arrays are just that. They're arrays without associated metadata. And so where Xarray comes in or if people have worked with pandas before, is you start assigning labels to your axes, essentially, and your coordinates, and then you can refer to data by its named dimension or coordinate, which is very convenient when you start working with especially large netCDF data sets. So again, for this 1D example, we're just going to take that array and wrap it into an xArray data array object. So now you see these same values here, and we've automatically assigned a dimension _0 because we haven't given it a name. But in effect, that is how these xArray data models work. Instead of automatically assigning a name, we can call it x because we know that this dimension is x. So we're dealing with a function f of x here. So we also have this concept of coordinates. If we tell xArray that the coordinates x are assigned to that dimension, then now you can see the representation of this array has the dimension labeled with the number of coordinates we have, and then the actual values of that coordinates are stored separately as the array x. So now we have f of x, but things are labeled. So now that they're labeled, there's a lot of things you can do more automatically. You can run plotting commands, for example, that automatically label your axes in terms of x, latitude, longitude, etc. So that is a very brief introduction to xArray. You can run through all of these cells, Shift Enter. I'm going to go through this pretty quickly to show a multi-dimensional example. So you can scroll down to where we have multi-dimensional data in the same notebook. And again, Shift Enter is going to actually execute some of these cells. So here we're loading a netCDF file. And xArray is really shines as an in-memory model for data that is stored as netCDF or HDF5 on disk. It's really about storing multi-dimensional data sets in memory. So here, instead of just a simple function of x, now we have multiple dimensions. We're dealing with latitude coordinates, longitude coordinates, and 12 time coordinates. So this is where people often talk about the data cube, and conceptually we now have a cube of information. And with those coordinates, we also have different data variables. So in this case, we have a single data variable, which is sea surface temperature. So we can visualize this really as a cube. And the syntax for working with these objects in memory with Python is really convenient for a researcher. You simply call everything by its name. So in this case, from our data set, we're wanting to look at the variable SST, which is sea surface temperature. So we're just no longer having to index things by 0, 1, 2, but instead use the names. That's the key concept with xArray. And metadata comes along for the ride. So if you have additional bits of metadata with your data set, that's also going to be coming with you in these xArray data sets. So you can index using these names as well. So if those of you who have used pandas before will recognize some of the syntax. You can use methods like select and specify a time just by giving a timestamp, and then plotting the result with xArray quite easily. And because it's aware of these additional dimensions and coordinates, you know by selecting a time that you're only left with latitude and longitude, which is why we get this plot now that's labeled of latitude, longitude, and in this case, color bar for the data variable we've asked for, which is SST. You can do other types of selections. So instead of selecting by time, we might be interested in a particular longitude. And now we're slicing this data in a different way, and we have longitude versus time through our data set. So it's very powerful to quickly explore multidimensional data. You can do more sophisticated functions and apply arbitrary functions to xArray data sets as well. So continuing down some of these columns, you see examples of of taking means, but specifying the axis that we're taking means across. So if you want to take the mean through time, you specify that we're operating on the dimension time with our mean. That means that we're going to get a plot back that's showing the mean sea surface temperature in our data cube for every latitude and longitude. So we get this map back. So there's more you can examine in this notebook. It's a nice simple walkthrough of how to work with a well-structured data cube with Xarray. I think now I'll illustrate how Dask works, and then we'll see the two coming together. So not sure what that was. Quick question. Yeah. Yes. So
if you look at the overhead of the problem.
I didn't hear the question, sorry.
So since you have the NumPy arrays behind the X array, what is the overhead X array bringing to you in terms of speed? Do you have any idea on that?
I'm not sure, to be honest. Things are, as far as I know, comparably fast compared to NumPy because the operations are doing NumPy operations behind the scenes. Okay, so Dask, as I mentioned earlier, is a Python package that's meant to easily distribute processing. So it's meant to make parallel processing easier. And it is a task manager, but it's also a cluster manager. So this notebook will walk through also using Dask, kind of building things up from scratch. So the key thing to Dask is that you can assign different types of clusters to use. If people have used Dask on a local laptop, you can launch a local cluster that will utilize all the cores on your laptop, for example. The really great thing about it and using to cloud operations is that it's simple to define a different cluster type. So as opposed to the local cluster, here we're defining a Kubernetes cluster, which is a way to assign machines on any major cloud service provider. So this could be Google Cloud, AWS, Azure. It works the same way. So we define a Kubernetes cluster, and then we can ask to bring up a certain number of machines. So you could think of this as cores, but in this case, we're going to ask for 4 machines by running the following code cells here. You'll see sort of a menu if you run that cell, and hopefully people are noticing that number of workers is jumping up. We requested 4, and so we see 4. And we also see the number of cores and memory available to us on that cluster. Dask then needs to connect to that cluster in order to utilize it. So this next code is going to connect to the cluster. And here we'll just see how Dask arrays work. So this is very similar to what we saw with Xarray, where we were just building up a simple array from scratch, but assigning it a label which defines it as a Dask array. In a minute, sorry, this is just a NumPy array. So this is an array that's 32 megabytes in size, so not that big. Dask arrays basically are constructed the same way. Instead of a NumPy ones and then the shape of the array, it's a Dask ones and the shape of the array. And you'll see, in contrast to what we see up here above, we actually get the values back because they're all in memory. Whereas Dask is designed to do things only when required. So it's going to basically save a reference to what that array is with ones, but not actually compute it until you need to compute it. This allows you to do things like farm off computations to different machines and then aggregate the results back at the end. So effectively what it does is it automatically chunks up NumPy arrays into smaller blobs that it can farm out to either different cores or different machines on the cloud. You can specify chunks in different way, and so there's always a lot of discussions on how to best define them, but generally you keep things to be several megabytes in size, up to maybe 10 megabytes in size. So depending on the data type and the array you're working with, you can define chunks differently. If you want to run operations on time axis, you can define chunks differently so that you're operating more efficiently with operations going through time versus latitude or longitude. But again, if we define an Dask array with chunks, anytime we try and visualize that array, we just see this reference to it without the actual values. But when you call specific functions like compute, Dask automatically does the computations and then brings it back into memory. So if you run the command visualize on a Dask array, you can see what's happening behind the scenes. In this case, we specified chunks of 1,000 by 1,000 on an array that's 1,000 by 4,000. So we've broken it up into 4 pieces. So we have to run a computation on each of those pieces and then bring the result back together. That's what's happening there. Sum of ones is not very interesting, but this is what Dask envisions as the sum of ones. You start with your 4 chunks, you sum those, you bring those together, you aggregate until you get to the final result. So you're generating tasks automatically of how to distribute these array operations. So I'm going to jump into, actually, if you scroll back up, when we created a cluster here, you got a link to a dashboard. And so if you click that link, oh, it's not working for me. Yeah, we're gonna skip that. Never mind. I can't show it. But you can see diagnostic information with Dask about what tasks are actually running. I'll show that in a separate notebook in a minute. But if we do bigger calculations with Dask, now you can work with an array that's 6 gigabytes, and you might be afraid of running out of memory in these types of operations on your laptop, and Dask is going to automatically do memory management as well. So if you start running out of memory on your machine, it will start writing to disk and reading from disk. So you're losing a bit of performance here, but you're really gaining a lot of functionality by not having to worry about the size of your data sets. So I'm going to jump ahead to another example that kind of brings this all together. And then we'll have some time for questions and your own work. So if we go back to those slides and launch the binder on AWS. So this was this Pangeo AWS demo. Did anyone click that link already? Great. And did everyone end up in a similar interface? I see some thumbs up. Excellent. So again, here we're running this same notebook on AWS. And so this is pretty cool. You get the exact same experience, but we're moving our computations around to where the data sets are. So I'm going to run this demo that kind of brings together Xarray and Dask to work with the Landsat 8 public data set that's on AWS. All right, so under the notebooks folder, people, I'm going to make this bigger because it got smaller again. Sorry about that. Maybe not. Okay, so under notebooks, you'll see this 0 demo AWS notebook. We can open that up. I'm going to close this tab over here. And this notebook illustrates, like I mentioned, a few of these kind of technologies coming together and working well together. So we're going to use a Python package called sat search, which uses stack catalogs that we've heard a little bit about today to kind of reference and locate data sets on AWS public storage. I won't be able to go into full detail about the code in each of these cells, but after I walk through this demo, we'll just have some time to experiment. You can put sticky notes up and ask more questions about this. So using this stack search tool, we're going to search for Landsat 8 data over Seattle. And so this is Python code to query this stack API and find Landsat data over Seattle. And Jupyter Lab has some pretty neat functionality to use interactive visualizations. So if we run through several of these cells up to this browse images cell, you can create interactive widgets pretty easily. In this case, we're just visualizing all the thumbnails for these Landsat 8 images that are over Seattle. So as you can see here, those are the frames of the images we're working with. So this is a stack of imagery, again, multi-dimensional imagery, but not climate or ocean data in this case, not modeling data, but Landsat scenes. So because this is running on AWS, all of this is very fast when you're accessing data in the same region. You can flip through images very quickly, get information about those images. It can be very useful for just getting a quick feel for data sets that are available to you. But what's really neat is now coupling this with the distributed clusters. And this is where this is the special secret sauce of these Pangeo JupyterHub deployments, is that we can launch these clusters and run analytic computations on big cubes of data. So there's this code here, which you could run to launch a cluster. I'm going to illustrate another way to do it. So if you've already run it, don't worry. If you haven't, comment this out. Commands / will do comments. And on the left here, we've, a group of people in the DAS community have created a tool to launch clusters in kind of an interactive way. So this little flying symbol over here is the logo for Dask. And you can click this plus new button to generate a cluster that way. Let's ask for just maybe 4 machines apiece, since there are a lot of us. If anyone asked for 100 already, if you could cancel that request by hitting shutdown, that would be appreciated. You can also select things like adaptive scaling. So if you start to hit memory limits, you're going to spin up new machines to accommodate the lack of memory that you have. But right now, we'll just all request 4, hit scale. And again, this may take a minute or two. It just depends on how many people are currently active on the cluster. And we haven't really set this up to accommodate large groups. We've set it up for kind of initial testing. There's no reason why you couldn't open this up to thousands of machines. Right now, we actually have limits that limit us to about 20 to 30 machines, in this case on AWS. So yeah, it can take a little bit of time, and we can't all request 100 machine clusters in this workshop because we'll run out of machines. So hopefully people will start to see number of cores and workers start to pop up over here. Let's give it a minute or two. Does anyone, actually I'll just poll right now. Does anyone see workers showing up for them? Great, so a couple. How many people have a cluster with workers showing up on it? Raise just a quick show of hands. And I imagine some people haven't tried, so that's okay. A few. Yeah, probably should have, but it's okay. We'll just, yeah. If people do want to try that adaptive approach under scale, you can say adaptive scaling, and then say minimum worker 1, maximum 4. That way, there's just more available to everyone at the same time. I'm going to just leave it as it is for now. You can see on my machine here, if you're not running it yourself and just following along on the screen, I now have 3 workers that have showed up for me. So that's 3 different, basically, machines that I have access to on this cluster. remember too, if you're having difficulties or weren't following along in some step, you can just put a sticky note on your laptop and we've got folks to come help out, try and diagnose issues. In any case, I'm just going to go ahead and run with this. So this cluster just showed up, but it's not actually connected to our notebook yet that we're running. So there's this maybe somewhat non-intuitive symbol here to inject the cluster into the notebook. And you'll see the code is just kind of generated that's necessary for you to connect. So this is the same thing we've done before, but we're just pointing to address to enter that cluster. So I'm now connected. As you can see in this readout here, there are also some nice diagnostics. On the upper left, you have these tabs for workers. So if you click on that, you'll see information about the machines that are currently available to you. You can also click on progress, which we'll see in a minute. We'll show you what's happening on that cluster or task stream. Feel free to just open a few of those tabs that are diagnostic tabs for Dask. I'm going to close that again so we've got a little bit more room. And we'll start running a few more codes to see how this works, code cells. So we're going to utilize an X-array library that we've been looking at. Raster.io is a great library for raster data. HVplot is part of the PyViz set of tools. And so these are really fantastic tools for interactive visualizations in a browser. Again, I'm not going to be able to go over all the details of how this works, but I'll just demonstrate quickly by running some of these cells. So here's a new X-array data set that we're loading, and we're loading a bunch of bands of Landsat 8 data. So each Landsat 8 image has bands stored within it. In this case, I'm just going to pick one band and load it into an X-array data set. You can see we do have some metadata coming along with us, like the projection. In this case, Landsat stored as a UTM projection. And we have X and Y coordinates instead of latitude, longitude, because we're in UTM. So often there's a bit of custom code you'll see written to load in satellite data. You have to specify which band, what it means, etc. Some of that metadata. If you run that next code, you'll see this task stream light up. And what's happening there is this is showing you operations that are running on that Dask cluster. So in this case, you can get diagnostic information about what code is actually running, but more than anything, it's just a useful way to visualize, all right, stuff's happening on this cluster. What's actually happening is because this image is kind of in predefined chunks, each of those chunks is getting mapped out to its own machine on that cluster. The computation's running. In this case, we want to visualize it. So it's just simply bringing it into memory and then, piping it to your browser for visualization. So that task stream is pretty handy for just knowing what's going on. So this is using PyViz, as I mentioned before. And unfortunately, I'm running out of room here, so we won't see necessarily all of this. But as I mentioned, these are great for interactive visualizations of large data. So this image here is a full resolution Landsat image. I believe this is band 1. You have tools within these PyViz visualizations to zoom in. And if you click on this box zoom, and we'll kind of, go up here on the Olympic Peninsula. As you zoom in, you may have seen that task stream light up again, and that's because we're pulling data that's appropriate for that zoom level. So you're accessing data at resolution that's appropriate for whatever visualization you're currently trying to do. So this is enabled because the Landsat 8 data is stored as a cloud optimized GeoTIFF format, which is pretty powerful for subsetting and being able to access and read only the pixels you're interested in. I'll go down and do a slightly more complicated example. People earlier in the big data session mentioned the fact that we can do a lot of things that traditionally have been done on a server now on the client side. So on your laptop, for example. Here's just a quick example of that. We're going to reproject from UTM to lat long, and it's just a matter of specifying the coordinate reference system that your data is in UTM zone 10 north for the Landsat data. And if we specify that, then as the data is pulled into memory, you're doing the reprojections for your coordinates. And so here we're now displaying things in latitude, longitude coordinates instead of UTM. Intake is a library I mentioned earlier that's designed to really facilitate getting these data sets into Python objects. So as opposed to the custom code we saw earlier, you can kind of put all the details needed to load an image into a file that defines how to load imagery from that data set. So now we have this catalog that sort of defines Landsat data on AWS, and you can just ask for certain bands, and that's all you need to load a data set into one of these Xarray objects with Dask. So I'm going to go through this pretty quickly here. This next cell, instead of loading a single band, we're loading all the bands, but only the bands that you're currently visualizing is actually brought into memory. So now this HV plot, these PyVis tools give us a slider, and we can start to march through the different bands for a particular image, maybe go to near infrared and see kind of how the visualizations change depending on the bands you're currently visualizing. So finally, there's just a quick example here running a more custom function to do NDVI on that entire cube of images over Seattle. So these next cells will run not on a single image with multiple bands, but selecting red and near infrared from every image in the archive through time, and then applying a simple band index on that larger array. So here, that Xarray data set is 120 gigabytes. So now we're starting to get into the realm of data it's not petabytes of data. We're not wanting to operate on the entire image archive, but many scientists, I would argue, are wanting to do exactly this and work with data sets that are cumbersome for the laptop, but really easy to work with on systems when it's in a cloud format. So here, our Xarray object, we have two bands, X and Y, and time. So one neat thing that maybe wasn't apparent when you load these data sets, Xarray also automatically adjusts the coordinates and will expand your X and Y to fit all those rasters, because they're not what people refer to as analysis ready data. They're not on a common grid, or they're on a common grid, but they don't necessarily have the same X and Y dimensions. One array might be 7,970. The next one might only have 7,960 pixels. Xarray is going to understand the coordinates and the dimensions and put them into a common grid for you. So now we have this larger data set. And again, when we visualize it or we use commands that we saw earlier, like compute for the mean or whatever aggregation you want to do against that data set, Dask is going to manage the computation on the cluster available to us. So what's really powerful about this is you basically go about the same style of programming. You're not defining how things are going to get mapped out to the clusters. You're just writing, I want to take the mean in latitude and longitude, or I want to reproject it, and the cluster is being managed behind the scenes. So now we're visualizing NDVI, and we again have a time slider where we can march through, in this case, in time, because we have calculated the NDVI for each Landsat acquisition, which is a different timestamp. So that sort of illustrates how these tools work together. It sounds like everyone was able to run this who gave it a try, which is encouraging. And we just want to leave the last, I guess there's 20 minutes now left in this session. for people to experiment on their own, and we can roam the room, answer questions. You can try some different computations and try and break things or see how many workers you can get before the system completely breaks down. But I'll ask right now too if there's just any other general questions about this before we just open it up for people to work a bit. So the question was, how hard is it to set up a Kubernetes cluster? That's what we're using to actually run all of this infrastructure, either the binder or these dedicated hubs. It's very easy on Google Cloud. It's harder on any other system. So you're welcome to talk to any of us here about that after the break. But generally, it's, I would say, a couple months effort from a few people in order to get it set up.
I guess, could you compare this to threads, and do you see this as a good substitute for using thread servers generally?
So I'll repeat this question and then go back to the next question in the back. But the question up front was, how does threads play into something like this? And I personally don't work much with threads. I haven't used it in my own research, but there's no reason why you can't access data on the same infrastructure that's available via threads. This infrastructure is especially powerful when things are co-located. So when the data is, if you're running this JupyterHub wherever the threads server is, then the movement of data is just so much quicker and more efficient.
So,
yep.
So suppose I don't have a cluster at hand, but I want to practice that. Does it have some sort of simulation or in-memory thing where it just uses your local PC's processors?
Yeah, exactly. There's you can launch what's called local cluster, and that's just going to map to your cores on your machine. And
Okay.
so you can also specify if you're wanting to use threads versus processes, and do experimentation that way.
Okay.
Okay, there's one other thing I wanted to mention, which is on these slides, there is a little survey at the bottom, the last slide. So we're just going to open it up now for you to work on your own. You can take an extended break if you want, but we're going to roam around and talk to people, answer questions. And there is this little survey. So if you click on that link, you know, the name, organization, email, if you don't want to put that in there, it's totally fine. But basically, we're more interested in just these, like, why am I interested? I'm excited to try something new that we showcased today. And then I'm still very confused about, you know, you name it. Because this is just an hour and we kind of scratched the surface of a lot of things. We didn't get into all the details, but there's definitely, being a like distributed project and system, there's a lot of confusion generally about what is what. And so if you just want to write those down, feel free to edit that spreadsheet with some feedback. We'd appreciate it. And yeah, thanks everyone again for coming. We'll just roam around now.